We will take applications of heat flow equations to lining design. Some of the applications I have already done in my earlier lecture. Now, today what I thought, I will try to illustrate the use of the equation in different units also, so that you are conversant with the units of various variables. So, I will give some of the say conversion values of the units. Say for example, 1 BTU, that is 1 British thermal unit, that is equal to 1.055 kilojoule. 1 BTU per hour, that is equal to 0.293 watts. Then 1 BTU upon hour feet square, that is equal to 3.154 watt per meter square. Then 1 BTU per hour feet, that is equal to 0.9613 watt per meter. Then 1 BTU per hour feet degree Fahrenheit, that is equal to 1.7307 watt per meter degree Celsius, that is the unit for thermal conductivity. Then 1 BTU hour feet square degree Fahrenheit, that is equal to 5.6782 watt per meter square degree Celsius, that is the unit for heat transfer coefficient. Now, with this, let us take another problem. Consider the design of a single wall refractory, single wall refractory tube furnace, which is operating at temperature Ti. While placed in environment at temperature T0. Now, you have to calculate critical insulating lining thickness. At which heat loss is minimum. Now, this problem I am given with the view that we always perceive that as you add more and more refractory lining, there will be lower and lower heat losses. That is what the perception of lining of the furnace is. It appears that it is not so, that you go on adding the refractory lining, the heat loss will continuously decrease. Now, let us see what are the factors that are responsible. So, in fact, the problem under consideration can be represented, for example, this is the tube furnace and this is the lining and this is the interline and this is the another view. So, we have, let us consider this, diameter as R2, this diameter is R1, this temperature is Ti, this is same here as R1, this is R2, and this is the refractory lining. This is the refractory lining, and if we wish to represent, say this temperature is T0, this is the environment temperature, not the temperature of the insulating environment interface. So, if we wish to draw the so called thermal gradient, then somewhere we have, say, this temperature, say this temperature, let us say this is T2, this is here T0, this temperature is T2, this temperature is T1, and here we have the so called this one, this, and this. So, this is the Hi, and here is the H0, they are the respective heat transfer coefficient. So, here the temperature is given of the environment temperature is T0. So, let us see how we get this concept of critical insulating thickness. Now, for this geometry, now say radial flow through the furnace wall, we already found, say Q, that is equal to 2 pi L Ti minus T0. Now, where this L, this is the L is the length of the furnace, upon 1 upon Hi into R1 plus 1 upon K ln R2 upon R1 plus 1 upon H0 upon R2. That is what we have already derived this equation. And now, if you look at this equation, R2, it represents the distance from the center of the furnace to the insulating lining. So, as R2 increases, then value of 1 upon H0 into R2, it decreases. That is, this 1 upon H0 R2 is the thermal resistance. So, as R2 increases, the thermal resistance offered by the heat transfer coefficient from lining to the surrounding decreases, but at the same time, the thermal resistance offered by the refractory lining, it increases. So, you see, the one parameter increase, another parameter decrease. So, there has to be somewhere a minimum value of Q. So, how will you find out? So, you have to differentiate this heat loss with the outer radius dr2, and we set this differential quotient to be equal to 0, and from there this you can do yourself, it is not a very difficult, and here we get R2C, that is equal to K upon H0. So, this relation represents that, well, there is a concept of critical layer thickness above which the heat loss will increase rather than it decreases. So, the prevailing concept that increase the lining thickness and you will decrease the heat loss, that is not true. There is a critical insulating thickness which depends upon the thermal conductivity of the material and heat transfer coefficient from the outer surface of the furnace to the surrounding. Now, for example, if we take K is equal to 0.06 watt meter Kelvin and H we take 6 watt per meter square Kelvin, then we get R2C, that is equal to 0.01 meter. So, what does it mean? That beyond a critical layer thickness of 0.01 meter, that is, if you increase the insulating thickness layer beyond 0.01, the heat transfer or the heat flow or the heat loss will increase rather than to decrease. So, for example, if we plot, say if we can plot here, we plot here say heat losses, we take ratio R2 upon R1. So, when R2 is equal to R1, then the heat losses will be very high. So, as we increase the value of R2 upon R1, then what will happen? The heat loss will decrease, and at some critical value beyond which it further increases. So, this value is the so called R2C upon R1. Now, this value, it depends upon the thermal conductivity of the material K1. Now, if I have another material which has a thermal conductivity higher than K1, then naturally this curve is going to have this particular way, where K2 is greater than K1. So, this is a very important concept in the refractory lining design, particularly for tube furnaces, that beyond a particular critical thickness, the heat losses, in fact, they increase. Also, if you couple this information with the thermal conductivity of the material, now you can also have an idea of selection of the material with reference to heat losses. Say, for example, if you have the different material of different thermal conductivities, this is the one way, then you select the material of lower thermal conductivity, or if you have a material of one thermal conductivity, then you can optimize with the increased layer thickness. So, what is important here is the concept of critical insulating thickness and the role of thermal conductivity of the material. That is, if you want to decrease the heat losses beyond R2, then you have to change the value of thermal conductivity. That is what this equation says. Now, let us take another example. Say, consider the design of a cylindrical laboratory electric resistance furnace that you must have done in your courses, because heating of the material in laboratory, we always use the tube furnaces. They are designed in the laboratory by winding a Kanthal wire on a ceramic tube. So, length of the furnace, is 0.6 meter. The outer diameter of ceramic tube is 0.06 meter, because you wound or you wind the heating element on the outer diameter of the tube. The insulation is fire clay brick inside and asbestos magnesia outside. The maximum temperature of heating coil is 1200 degrees Celsius at 750 watts at steady state. Now, it is also given that asbestos magnesia can sustain a maximum temperature equal to 850 degrees Celsius. You have to find out or determine the thickness of two insulating layers when the total insulation thickness is minimum. Now, that is very important, that is you have to find out the thickness of both layers at which the total thickness is minimum. That is where the key of the problem lies. So, also it is given, say K fire clay, that is given to you 0.72 watt per meter Kelvin. K asbestos magnesia is given 0.12 watt per meter Kelvin. Also assume 25% of total power is lost, and also outside wall temperature of the furnace assume at 40 degrees Celsius. So, what we have to calculate the total thickness at which the insulation thickness is minimum. So, what we have to do now, again we have done already the composite cylindrical shell, and we can write down these equations. For example, if I represent it, that this is what is required to be done. This is the tube furnace, this is a ceramic tube, and this is your fire clay brick. This is the fire clay brick lining, and here this is the asbestos magnesia lining, and say if we represent another view here, then this is our furnace tube, this is the fire clay brick lining, and this is the asbestos brick lining. So, let us take it, this is as R1, this is as R2, and this one as R3, right. So, similarly, we can also say this one is here R1, this is R2, and this is R3. This temperature is given 40 degrees Celsius, and this temperature is given is at 1200 degrees Celsius. That is the maximum heating element temperature, and the length of the furnace, that is given to you is 0.6 meter. R1 is equal to, R1 is given to you how much, that is outer diameter, that is the 0.06 upon 2, that is meter, that is. So, we know this equation, T1 minus T0 upon Q, that is equal to ln R2 upon R1 on 2 pi Lk fire clay plus ln R3 upon R2 2 pi Lk asbestos, where here this temperature I am taking as T1 and this temperature is T0. Now mind you, here we do not need the value of heat transfer coefficient because the temperatures directly at the interface is given. So that is why I have not used the interface the heat transfer coefficient. Now it is said that the asbestos magnesia can sustain a maximum temperature of 850 degrees Celsius. This one is asbestos magnesia and this one is fire clay. So when this can sustain, this asbestos magnesia can sustain maximum of 800 degrees Celsius, that means the interface temperature between asbestos magnesia and fire clay is 800 degrees Celsius. So with this we can write down, say, T1 minus T2 upon Q, that is equal to ln R2 upon R1 2 pi L K fire clay. Now this temperature, the interface temperature, I represented as T2. Now all that I have to substitute these values, then I will be getting, so T1 is 1200, T2 is 850, just now we have discussed. What is the value of Q? Q will be equal to 750 watt supply, 75% is used, that is the value of Q. So you can substitute all the values. So we will be getting R2 is equal to 0.162 meter, and hence thickness of fire clay, that will be equal to 0.132 meter, because R2 value is from here to here, so we have to subtract the value of R1. So that is how you can get. Now since the value of R2 is known to us, now we can use of this particular expression. R2 is known to us, we have to find out the value of R3, rest everything is unknown. You substitute the values of all, then you will be getting R3, that will be equal to 0.311 meter, and so thickness of asbestos lining, that will be equal to 0.149 meter. So that is the answer. Now what is required in this problem to think? One, as the problem says that you have to find out the thickness of two insulating layers when the total insulating thickness is minimum. Now this particular means, if you note that the value of K asbestos, say K asbestos is very much less than the value of K fire clay. So that means if total thickness has to be minimum, then the lining of asbestos magnesium has to be higher. Number one. Number two important point in this particular problem, that the maximum temperature which asbestos magnesia lining can sustain is 850 degrees Celsius, and this particular information directly tells you that the temperature at the asbestos magnesia and fire clay interface is 850 degrees Celsius, and these are the two important things that are hidden in this particular problem. Unless you dig out, it will be difficult to solve the problem. So that is what this idea. Now let us take another problem. Say a long electrically heated cylinder, say 1 inch in diameter. Now I am illustrating a problem in British units, is covered with 3" of insulation, 3" of insulation in which K is given to you 0.05 BTU feet square hour degree Fahrenheit. The temperature in the insulation, varies from 800 degree Fahrenheit at the inside surface, to 240 degrees Fahrenheit at outside surface. Now find what is the heat loss. What is the heat loss in watt per running feet? Now purposely I mix the various units so that you bring your attention while solving the problem, and at the same time you are conversant with the different type of units. Now to solve this problem is very straightforward, because here you have to use the simple expression, that is the heat flux or rather heat loss Q, that is equal to T1 minus T2 upon ln R2 upon R1 divided by 2 pi L K1, or you can also put it that is equal to 2 pi L K1 T1 minus T2 upon ln R2 upon R1. Now if you want to represent, very simple, say this is the furnace and here we have the insulation. This is the insulation. Now this is given as 1 inch diameter, and this is given as 3 inch insulation thickness. Or if you wish to represent somewhere here, then this is the furnace tube and this is the insulation. So this diameter is 1 inch, and from this thickness or from central line, this is 3.5 inches. So we are given this temperature is T1 and this temperature is T2 and this length is L. So I have written this expression. All that you can substitute, and the heat loss will be equal to 90.36 BTU per hour, which is, that will be equal to 26.43 watt per running feet. BTU per hour per running feet. So that is how you can solve this particular problem. Now as an extension of this problem, part B, I would like you to calculate, say make the calculations, and plot insulation temperature, versus distance from cylindrical axis, cylinder axis. So, what is required is that if suppose this is 1 inch and this is the those sides 3 inch as given, this is 1 inch. So, what is required? You have to plot, you have to calculate the temperature at various distances in the lining and then you have to plot. For example, if we take this is 1 inch, this is 3 inch, we have to use the formula. You know this, that Q that is equal to T1 minus Ti into 2 pi k upon ln Ri upon R1. So, what I represent? I am representing this is as Ri and this is as R1. So, that is what I am representing over here, and this is as your T1 and sorry, this is as T1 and we have to calculate Ti, we have to calculate Ti as a function of the distance from the cylinder axis. So, what we will do? We will simply, we know the value of Q, of course, this is per meter. So, we have calculated Q 90.36, that is equal to 800 minus Ti into 2 pi k upon ln Ri upon R1. So, I will substitute the various values. For example, I take Ri and I calculate Ti and then the insulation thickness. The insulation, because insulation thickness you have to subtract the diameter of the tube. So, Ri, if I take say 1.5 inch, take here 2.5 inch and 3 inch. So, Ti will come 484 degree Fahrenheit, 337 degree Fahrenheit and 285 degree Fahrenheit. Insulation thickness will be 1 inch, here it will be 2 inch, here it will be 2.5 inch and at Ri is equal to 3.5, insulation thickness is 3 inch. What will be the temperature? This is at 240 degree Fahrenheit, that is given. So, this temperature is given as 240 degree Fahrenheit. So, now all that you have to plot, well, you should plot on a graph paper. So, if you plot here, say let us take here temperature and here we will take the so called value of Ri. Then at Ri is equal to 0.5, the value of T is 800. That is, here the value is given to you 800 degree Fahrenheit. So, at value 0.5, this is at 800 degree Fahrenheit. So, that somewhere here is 3.5. So, at 3.5 I have value of 240, then I can plot and it appears to me somewhere a slightly non-linear nature is supposed to be there. So, that is what you can also plot and see how the values are varying. Another, let me illustrate now the role of air gap, as I have told in my lecture that I will illustrate it through a problem. So, let us see, say in laying refractory bricks, in laying refractory bricks, in a furnace, it is observed that two courses of fire brick 2 courses of fire bricks, K that is equal to 1.5 BTU feet square into hour into degree Fahrenheit are poorly joined, so that a 2 millimeter air gap is created. Because when you make a wall, then you lay one brick after the other and the next brick and next brick. That is what the furnace wall is. So, in laying the 2 bricks, sometimes because of the roughness or whatever mistake you have done, a space between the 2 brick is left, and that has a width of 2 millimeter. So, that a 2 millimeter wide air gap is created. The brick temperature in the vicinity of joint is 1000 degree Fahrenheit. Now, estimate the additional brick thickness, in inches to which thermal resistance of the joint is equivalent. Now, you are laying 2 bricks and in between there is an air gap. So, what then air gap can do? Because of the very poor thermal conductivity of the air gap, the temperature will drastically fall between the brick. So, as the next brick, if it cannot sustain the sudden temperature fall, then this brick may collapse. So, that is what the importance of air gap. And the air gap which is left over, that is, for example, in this particular problem 2 millimeter, how much amount of thermal resistance it is equivalent to, that we can calculate now. It is given K air is given 0.018 BTU feet upon feet square hour and degree Fahrenheit. Now, you can calculate this particular problem by 2 ways. Either you take the thermal resistances of air gap, thermal resistance of the brick and calculate the thickness, or you can also calculate the heat flow through an air gap and heat flow through the refractory. So, either of the way is okay. So, let us take it now. So, let us say the thermal resistance of air that will be equal to delta x upon K into A. That is what the definition of thermal resistance, delta x that of the air. Now, the thermal resistance of brick, that is equivalent, that will be equal to delta x brick upon K brick into A, where this is K of air. So, this delta x B is an equivalent thermal resistance. So, therefore, we can have delta x air upon K A into A, that is equal to delta x B upon K B into A. So, from here we can calculate say, then we can calculate delta XB, the AA gets cancelled, that will be equal to KB upon KA into delta X air. Now, delta X air, that is equal to 2 millimeter. To convert into inches, KB and KA, they are all given. So, we can find out delta XB, that is equal to 3.8 into 10 to the power minus 3 feet, that is equal to 0.046 inch, that is equal to 1.16 millimeter. So, an air gap of 2 millimeter thickness is correspond to an additional brick of 1.16 millimeter thickness. So, that is what the importance of. Now, last problem I will like to say, or I will like to illustrate, say consider the design of the following lining, of the following lining. Now, this is a composite wall construction, it is a composite wall. So, we have this is a refractory wall, this is another refractory wall. Say this refractory wall consists of fire clay and this one is insulating brick. The insulating brick. Now, this has thickness 9 inch and this has thickness 4.5 inch. Okay. Now, here K average is given to you 0.8 BTU feet degree Fahrenheit and the K average is given here 0.1 BTU feet degree Fahrenheit. So, this is a composite wall construction and a composite wall made of two types of refractory bricks. One is fire clay which is 9 inch thick and another is insulating brick which is 4.5 inch thick. Now, the temperature of the fire clay brick facing the combustion chamber of the furnace, that is the temperature at the combustion chamber and fire clay interface, that is here, is given to you 2050 degree Fahrenheit. With this it means you do not require the heat transfer coefficient value, because this is the temperature at the combustion wall, at the combustion chamber and fire clay interface. Now, similarly, at the insulating brick and environment interface, the temperature is given, that is here 350 degree Fahrenheit. So, you do not require any heat transfer coefficient value. So, this is the problem, and now what you have to calculate, say calculate heat flow through the wall. Heat flow through the wall, of course in units BTU per feet square hour. So, naturally you have to assume here 1 feet square you have to calculate. So, you can do this problem and the answer of this problem will be 362 BTU feet square hour, and this is the answer of this particular problem. This is A. B, calculate temperature at joint of fire brick and insulation. So, The answer for this question for this part will be T1 or T, that will be equal to 1664 degree Fahrenheit. C temperature 2-inch back from hot surface of the fire break. Hot surface of fire break. So, this will be, answer will be 1975 degree Fahrenheit, that is the answer. D, temperature at midpoint of the insulation, at midpoint of insulation. So, this temperature will be 985 degree Fahrenheit. So, this is the answer. So, with this illustration, I have sufficiently illustrated the use of heat flow equation for design of the furnace lining. Now, by now you must have gotten a feel the important role of heat transfer. What we have learned so far is that how to optimize the lining thickness and integrate it with the available materials of different thermal conductivity. The heat losses in the furnace lining design can be minimized either by increasing the value of thickness or decreasing the value of K. Now, which one, whether you will decrease the heat loss by increasing the lining thickness or by decreasing the value of K, it will depend upon the availability of the material and the cost consideration. Because if you want to have a material of low thermal conductivity, it has to be produced, it is porous and it may be slightly expensive. If you have a material of high thermal conductivity, well, those materials should be used where the temperature requirement is also important. So, what I mean to say here, that there are several factors which must be optimized in order to come a particular refractory lining design, and on the top of it, it is also important that the phases which are in contact with the refractory material is also an important issue. So, this is what I was able to illustrate. Now, the next topic that I will like to go on, convection. Now, another mechanism of heat transfer is convection. As already I mentioned in my introduction, that convection is essentially fluid flow. In heat transfer by convection, fluid flow is important. Depending on the type of flow, heat will be transferred faster or at a lower rate. So, with the faster movement of fluid, the faster transfer of energy. So, the convection is associated with fluid motion. In fact, when a packet of fluid of higher velocity transfer, it goes to the lower velocity, then their heat transfer will again occur by conduction. So, in fact, the mechanism, if you talk of the mechanism of heat transfer, then even in convection on the molecular level, it is again the heat is being transferred by conduction. In fact, the role of convection is in the fluid flow. So, the convection is associated with fluid motion. So, accordingly, we have natural convection, which is also called free convection. Natural convection, now here the fluid movement is due to temperature difference. Now, for furnace design, the natural convection is important from the heat loss from the wall of the furnace to the surrounding. Higher is the temperature of the wall, higher will be the heat losses, and there the heat loss predominant mechanism from the heat loss from the wall of the furnace to the surrounding is by natural convection. Another is say called forced convection. Now, as the name suggests, you are forcing the fluid to move, you are applying some type of force. Naturally, the fluid flow will be faster, and as the fluid flow is faster or the velocity is faster, there will be faster mechanism of heat transfer. So, for example, blowers, pumps, fans, all they rather induce the fluid to move, and as a result of which the transfer of heat occurs. Now, say one of the important thing in case of convective heat transfer or in the application of the convective heat transfer is to know the temperature, because if we know the temperature, we can determine the heat loss and so on. Now, there are few ways in determining this temperature. One of the way is to do the differential energy balance and couple it with the Navier-Stokes equation. This is the most fundamental approach, but this approach will require the numerical solution of the coupled equation, because you have to couple the fluid flow equation, that is the Navier-Stokes equation, with the energy equation. Then you can find out the temperature, and from the temperature you can find out the so called heat losses or whatever you can want, you can do whatever you like to do it. Another approach is based upon the heat transfer coefficient. Now, for most engineering calculations involving convection, the concept of heat transfer coefficient is very often employed in order to determine the heat losses. In several cases, for example, the heat transfer from POC or products of combustion to the charge, there you may not require the detailed knowledge of convection, but all that you require how much amount of heat is being transferred. Similarly, a body of the gas is flowing over the liquid or flowing of the surface, we do not require, or we may not be requiring a detailed knowledge of convection mechanism so on, but what we are requiring is simply how much amount of heat is being transferred. So, for all these purposes, the approach of heat transfer coefficient has been found to be very useful. Now, as such, in the detailed study of the convection as applied to furnace design, we will be taking the approach of utilizing heat transfer coefficient to estimate the heat losses. Now, here care must be exercised that heat transfer coefficient is an empirically determined constant. Mind you, it is not a constant like density, like thermal conductivity, like it is not a property of the fluid. It is an empirically determined constant which depends upon so many factors: geometrical arrangement of the surfaces, cooling behavior, temperature difference. All these are the important factors which govern the so called heat transfer coefficient. The further application of the heat transfer coefficient we will take in the next lecture.